In Module 6, we're going to talk about atomic structure and periodicity and the failures of classical physics in describing the nature of the atom. So in the first, we're going to talk about classical mechanics and the breakdown of classical mechanics, and you'll need to be able to define the following terms: wavelength, frequency, electromagnetic radiation, hertz, and spectrum, and state the relationship between wavelength and frequency, memorize the speed of light, classify radiation from shortest to longest wavelength, know the colors of the visible spectrum, and know the wavelength range of the visible spectrum. So electromagnetic radiation is simply the transmission of energy through space, or what we call light. Now, this is actually two waves put together. There is what we have the electric field and the magnetic field, hence the term electromagnetic radiation. And what it is we have this sinusoidal wave in both the magnetic and the electric field. That is how the energy is carried. Now, waves are characterized by a few different things. Wavelength, or lambda, the Greek letter lambda, is the distance between two equivalent points on a wave. So you can see here the wavelength of this piece of electromagnetic radiation is between where it touches zero and the next time it touches zero on the upswing. In other words, from crest to crest or trough to trough. Frequency is another way that we measure a wave, and frequency with the Greek letter nu, that is not a V, that is a nu, is the number of waves passing by a point per given unit of time. And the wavelength times the frequency gives you the speed, and the speed of light is a constant at 3.00 times 10 to the 8th meters per second. That's the usual value that people memorize these days. It's actually 2.998 something meters per second. That means that wavelength must be in meters and frequency must be in inverse seconds. Now, inverse seconds is also known as the hertz, for the gentleman Hertz, who the unit is named after. So inverse seconds or hertz, they're exactly the same thing. So let's use this relationship to determine characteristics of a wave. The laser in an audio CD player uses light with a wavelength of 7.80 times 10 to the second nanometers. Calculate the frequency of this light. Okay, so C is equal to lambda times nu. Now, C we know is 3.00 times 10 to the 8th meters per second. So all of my other units have to be in meters and seconds. The wavelength we have is 7.80 times 10 to the second nanometers. Well, I want to convert that to meters. So 1 meter is 10 to the 9th nanometers, and this gives me 7.80 times 10 to the minus 7th meters. And we want to find what is nu. That's the question. So C is equal to lambda nu, or nu is equal to C over lambda, and 3.00 times 10 to the 8th meters per second over 7.80 times 10 to the negative 7th meters gives us 3.85 times 10 to the 14th inverse seconds, or hertz. Now, electromagnetic radiation carries through a lot of different wavelengths and frequencies through what we call the electromagnetic spectrum. And here we have the electromagnetic spectrum going from a wavelength in 10 to the minus 12 meters all the way up to 10 to the 4th meters. So down from very, 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 very small wavelengths to very, very large wavelengths, over kilometer-sized wavelengths. So the lowest wavelength is gamma rays. Okay, gamma rays are used for a lot of different things. They are used to help preserve foods. That's one of the reasons. It's also background radiation from the Big Bang. Then at about 10 to the minus 10 meters, we have X-rays. And then after X-rays, at about 10 to the minus 8th meters, we hit the ultraviolet. Ultraviolet radiation is what gives you skin cancer. So UV radiation, the bad stuff. X-rays, I didn't think I needed to tell you what we use X-rays for. And then we have this small region from about 400 nanometers to about 700 nanometers. And this goes a little bit fuzzy because different people can see different wavelengths of the electromagnetic spectrum. Some people can see more blue or more red. But from 400 to 700 nanometers, we have what we call the visible spectrum, what we consider light. And the colors of the visible spectrum are Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. Okay? After the visible spectrum, we have infrared. Infrared is heat radiation. So when you feel the sun hitting your skin and it gets warm, that is the infrared radiation. About 10 to the minus 2 meters, we hit microwaves. Microwaves we use to cook our food. And we also use it for communication, things like satellites. Then we move on to the meter size or even larger, over kilometer size. These are radio waves, and we have FM radio to AM radio. And these are really, really big, large electromagnetic waves. Now, the interesting thing is all of these waves move at exactly the same speed, the speed of light. Okay? So you need to be able to pick out the individual bits of the electromagnetic spectrum, particularly this visible region here, the 4 times 10 to the 7th, 4 times 10 to the minus 7th meters to 7 times 10 to the minus 7th meters, or 400 to 700 nanometers. In section 2, we're going to talk about the failings of classical mechanics. So we're going to discuss the black body problem in simplest terms, discuss Planck's contribution to energy. You'll have to memorize Planck's constant. Calculate energy of light from wavelength or frequency. We'll talk about the photoelectric effect and describe Einstein's wave-particle duality of light. We'll calculate quantities such as work function, kinetic energy, velocity, frequency, etc. for photoelectric effect problems. You'll also need to be able to calculate the de Broglie wavelength for a particle, and we'll discuss interference and diffraction in simplest terms. Alright, so black body radiation, the black body problem, was a problem in physics that had stumped many, many physicists. And in its simplest terms, a black body is an ideal system that absorbs all the electromagnetic radiation frequencies that hit it. In other words, it is perfectly black. But for a system to be able to absorb all of those frequencies, it must then also be able to emit all those frequencies. Okay? And that's pretty simplistic, but we can talk about this in terms of heated solids. Okay? If we heat a piece of metal to the point where it starts to glow, we say that is incandescent. Okay? And the frequency or the wavelengths of light that it emits are temperature dependent, and they're dependent upon the material. Now, this is a problem, okay? And you can read more about it. Wikipedia's got a great article, but very highly technical on the black body problem. But suffice to say, classical physics fails. It cannot adequately describe the incandescence of materials. So enter Max Planck. And Planck's solution to the black body problem was to state that energy is not a continuous function, that it exists in discrete packets that he called quanta. Okay? This is actually pretty simple to understand if you think about energy being like a staircase. You can't move up a half a step. You have to move up whole steps or multiples of whole steps. It's the same with energy. You can't have a half of a quantum, half of a little packet of energy. You either have to have a single packet or 2 packets or multiple packets. Now, this led to Planck's constant, which we give the symbol h. And Planck's constant has a value of 6.626 times 10 to the minus 34 joule seconds. And that means that the energy associated with our electromagnetic radiation, or the change in energy, or energy there, is equal to Planck's constant times frequency, because frequency given in inverse seconds times joule seconds gives you joules. So we can calculate the amount of energy in light by using Planck's constant and the frequency. So let's do a calculation. A photon of ultraviolet light possesses enough energy to mutate a strand of human DNA. What is the energy of a single UV photon and 1 mole of UV photons having a wavelength of 25 nanometers? They also tell us that 1 mole of UV photons is equal to 6.022 times 10 to the 23rd UV photons, which we should already know that because that is Avogadro's number. All right, so we'll talk about what a photon is. Consider it just a discrete packet of light. So we know we're looking for the energy of a single photon. So the energy is equal to h times nu. But we're not given the frequency. We are given a wavelength. Well, we know that c is equal to lambda times nu. If I rearrange c equals lambda nu for nu, I get nu is equal to c over lambda. If I then substitute that back into my energy equation for nu, I get E equals hc over lambda. This is another form of the equation that you might want to remember. It's useful when they're giving wavelengths. Now, remember that in this chapter, all of our units have to be in the SI system because this is physics. We need to have things in meters, masses need to be in kilograms, energy needs to be in joules, times need to be in seconds. All right, so we've got 25 nanometers. 25 nanometers times 1 meter is 10 to the minus 9th nanometers, gives us 2.5 times 10 to the minus 8th meters. So I'm going to plug that into my energy equation here. E is equal to 6.626 times 10 to the minus 34 joule seconds. That is my value for h, times my value for the speed of light, 3.00 times 10 to the 8th meters per second, over my wavelength of 2.5 times 10 to the minus 8th meters. And I'm going to get an answer in joules. And that is 7.95 or 8.0 times 10 to the minus 18th joules. Okay, so 8.0 times 10 to the minus 18th joules with two significant figures. That is the energy associated with one of these tiny little particles. Just one. Now, if we want to find out for a whole bunch of these particles, then I'm going to take that energy, 8.0 times 10 to the minus 18th joules per photon, and I want 1 mole. So 1 mole of photons and 6.022 times 10 to the 23rd photons. That way the photons cancel. I get joules per mole of photons. And that gives us 4.8 times 10 to the 6th joules of energy for 1 mole of these photons. Another problem that plagued classical physics was this concept of the photoelectric effect. And a photoelectric effect was the observation that when light of a specific wavelength hit a piece of charged metal, it could actually eject an electron off the surface. That's hard to understand if light is a wave, but it's not so hard if we can think of light in terms of a particle. Now, the photoelectric effect, you have to have a minimum amount of energy. Now, any extra energy, so for example, if you have something with higher energy, the extra energy that is imparted to the electron goes to speeding it up. So we can actually see that here in terms of the diagram, that red light, 680 nanometers, which is actually lower in energy than blue light at 420 nanometers, no electron gets ejected because there's just not enough energy to pull that electron off. At 540 nanometers, the electron is ejected. Now, this says 550 nanometers, but 550 nanometers wouldn't have enough energy to eject, so I think this is a typo on the picture. But energy that is green, let's say 530 nanometers, let's pretend that's 530 nanometers, we can eject an electron because it is greater energy than the minimum energy needed to pull the electron off, and some of that extra energy goes to speeding up the electron. If we use blue light at 420 nanometers, which is much more energetic than the minimum of 540 nanometers, the extra energy goes into the movement of the electron. Now, this was all solved by good old Albert One Mug. Yes, Albert Einstein. And this is actually what Einstein won his Nobel Prize for, his work on the wave-particle duality of light and the photoelectric effect. So his conjecture was simply that light behaves as waves and as particles, that it does both. It's wave-like in terms of things where we want it to behave as wave, classical mechanics, and it's particle-like if we use the concept of quantization of energy. And we used the word photon before. I said that's basically a little packet of energy. Well, this is light behaving like a particle. And each of those particle light packets are quantized. Now, these photons can interact with electrons to eject them from the metal surface. So what we have is, depending upon how you are measuring light, it can behave like a wave, or it could be like a stream of particles. All right, so the energy of the photon is equal to h nu. We know that c is equal to lambda nu, so the energy of the photon is equal to hc over lambda. We've already derived that equation, but it's nice to see these guys again because you will be required to know them and use them. So going along with the photoelectric effect, we have a minimum frequency needed to eject an electron, a minimum amount of energy. We call this the threshold frequency. And the minimum energy is often called the work function, or given the Greek letter phi. And this is related to the minimum frequency by E equals h nu. So the frequency and the energy of any packet of light, a photon, that strikes a charged piece of metal needs to exceed the minimum to eject the electron. And as I said, excess energy goes into accelerating the electron. In other words, we can write this as the energy kinetic of the electron is equal to the energy of the photon minus the energy required to eject the electron. So let's do a calculation. The work function of an element is the energy required to remove an electron from the surface of a solid element. Now, just to point out, the work function of different pieces of material are going to be different. So the work function for lithium is 279.7 kilojoules per mole. That is, it takes 279.7 kilojoules of energy to remove 1 mole of electrons from 1 mole of lithium atoms on the surface of lithium metal. And again, I love how they're telling chemists that 1 mole is equal to 6.022 times 10 to the 23rd atoms. What is the maximum wavelength of light that can remove an electron from an atom of the surface of lithium metal? So we need to know the maximum wavelength of light. We know the work function is 279.7 kilojoules per mole. So 279.7 kilojoules per mole. Let's rewrite that. 279.7 kilojoules per mole. Now I want to find out what the wavelength of that one single photon is. So I'm actually going to turn this, number one, into joules. So 1,000 joules is 1 kilojoule. And then I'm going to turn it into one particle. So 1 mole of photons, to cancel the moles, is 6.02 times 10 to the 23rd photons. So we're going to find out the energy per photon, and that gives us 4.65, and actually let's use the correct number of significant figures here, 4.646 times 10 to the minus 19th joules per photon. So that's the minimum amount of energy required. So this energy is going to equal hc over lambda. We're looking for lambda, so lambda is equal to hc over E. Let's plug in our numbers. 6.626 times 10 to the minus 34 joule seconds. That's a Planck's constant. 3.00 times 10 to the 8th meters per second. That is the speed of light, divided by this energy, 4.646 times 10 to the minus 19th joules. And we're going to end up with 4.279 times 10 to the minus 7th meters, or 427.9 nanometers. Alright, so now we're going to talk about diffraction. And diffraction is a pattern that happens when we have constructive or destructive interference. Now, it's pretty easy to understand constructive and destructive interference when we talk about light as a wave. So constructive interference is when we have two waves that are in phase such that the peaks line up with the peaks and the troughs line up with the troughs. What that does is it doubles the intensity. It's an increased bright spot that we would see. And then if we have destructive interference, this is when a trough and a peak come together. They cancel each other out, and we get a decreased intensity. Diffraction is based on the interference pattern of light. Now, we can use this for a whole bunch of different things, but suffice to say it's really, really interesting that we can have something like this, that picture, which could be made, I'm not saying this is made, but it could have been made by the interaction of laser light with a surface. And if that were to occur, lasers are like light behaving like a particle. So you actually get particles that can constructively and destructively interfere with each other, which is really, really strange. I'm not going to go into a whole lot of depth on this, but suffice to say, there are a couple of experiments that you should dig a little deeper on. The single slit and the double slit experiments. So you should dig into the single slit and the double slit experiments. This is really fascinating stuff. Unfortunately, time constraints do not allow us to delve into the cool nature of this this failing of classical physics. Okay. Another thing that diffraction is, and you've seen diffraction, is when you have a CD player or a CD or a DVD or even a Blu-ray, when you see the different colors of the light that show up on the surface, that comes from interference patterns along the metallized surface of the CD. So that's actually how CDs and DVDs and Blu-rays actually store information, is pits and high points on a metallized surface. It's kind of interesting. Anyway, what this leads to is the concept put forth by de Broglie. And what he said was, if light can behave like a wave and a particle, why can't particles have wave-like properties? Okay? And this leads us to the concept of the de Broglie wavelength, or de Broglie wavelength, which is equal to h over mv. Now, this is mass and velocity, not frequency. Mass times velocity is equal to what we call momentum. So this is h over momentum. Now, only small particles can have a verifiable de Broglie wavelength. Big things, that wavelength is just too small. Because remember, the size of h is really, really small. 6.626 times 10 to the minus 34 joule seconds. That's an incredibly tiny number. You need something that's moving really, really fast and is incredibly tiny to have an appreciable wavelength. So let's calculate the de Broglie wavelength for the following. An electron with a velocity of 10% of the speed of light and a tennis ball served at 35 meters per second. So let's tackle part A. The de Broglie wavelength, and I'm just going to write capital D, is equal to h over m times v. Well, the velocity here is 10% of the speed of light. So this is going to be velocity is equal to 0.10 times 3.00 times 10 to the 8th meters per second. So our velocity here is actually 3.00 times 10 to the 7th meters per second. And the mass of the electron is 9.11 times 10 to the minus 31 kilograms. That is a constant that can be found in your book. So the de Broglie wavelength D, is equal to 6.626 times 10 to the minus 34 joule seconds over 9.11 times 10 to the minus 31 kilograms times 3.00 times 10 to the 7th meters per second. And this gives us 2.4 times 10 to the minus 11 meters, which is incredibly small in terms of a wavelength. However, when you consider that this wavelength is quite large compared to the size of an atom, this is an appreciable de Broglie wavelength. Let's do part B, where we have a tennis ball, 55 grams, served at 35 meters per second. So the de Broglie wavelength for part B is going to equal, well, our velocity is 35 meters per second. Our mass is 55 grams, but it has to be in kilograms, so 0.055 grams. And h equaling 6.626 times 10 to the minus 34 joule seconds. So the de Broglie wavelength of the tennis ball is equal to 6.626 times 10 to the minus 34 joule seconds over 0.055 kilograms. I should have been in kilograms there. And then 35 meters per second. This gives us 3.4 times 10 to the minus 34 meters. Now that is not an appreciable wavelength. Okay, how do I know? Well, part A, 2.4 times 10 to the minus 11 meters, that puts us in the X-ray category. Past X-rays, down to 10 to the minus 12 or 13 meters, was the gamma rays, and that is the beginning of our electromagnetic spectrum. 10 to the minus 34 is way too many orders of magnitude smaller than our smallest known electromagnetic radiation. Therefore, the de Broglie wavelength of macroscopic substances is negligible.